this is where I left off a bit frustrated because of me not being really satisfied with the explanations that were given around what the Control Z is. And in terms of game dynamics, the explanations given in the article are okay, but at the end, it's a bit basically teasing you to try to figure out that by using the Q experience, and that's exactly what I'm going to do. So I don't know. I have been playing with that before. Let's see what happens. But I'm not really an expert in that. And at the end of the day, what I want to try to understand is what is intuitively the Control Z, because I have the impression that when we think about the control not operation, it has something to do with creating a certain type of correlation between two qubits, a certain type of entanglements between two qubits. And so let's check it out. So I'll just open the IBM quantum computing. I'm going to be using the beta experience. I think it's way better than the one before, and I like it more. I've been using it a little bit, but also not extensively. So let's see. And I might probably make a separate video about everything else you can do here, and maybe going through the guides, which seem to be also pretty interesting. But let's get to the point. So I'm just going to open the circuit composer, and I'm going to call that experiment understanding the Control Z. Good. So a bunch of stuff already in here available. That's interesting. How do we even go about that? So one of the things that I figured out while playing with this is that the way I can just reduce this thing to 2 qubits is I can just do like that, and I think that's going to make it easier first. Let's see. So let's see. First, let's try to play with what I know already, which is the control knot, right? But I mean, just a control knot, really nothing. Let me see what I can do here. If there's some sort of, I remember there were some sort of visualizations. Oh, cool. Oh, that's cool. Can I make that bigger? No. Okay. State vector, density matrix. I wonder if that density matrix has anything to do with the the matrix that, so this in here, right? This grid in the middle. I don't know what a density matrix is conceptually, but it looks like it's something to do with that, because basically it says the probability of getting 0, 0 and 0, 0. But why does it say 1, 1 and 0, 0? Because I would say that's 0, 0 and 0, 0. Because I mean, both are zeros, so the control knot is not going to take any effect. Okay, let's see. But so for example, the way to create the entanglement that I was talking about is by doing something like that, right? Cool. So now you see basically that so given that, and I'm assuming what this is telling you is if you would just do a normal measurement on the Z, so this measurement here, nothing else. And here we have another grid, which I don't know what is this for. It's a bit, okay, let's see. So this basically is telling me that the probabilities of getting 1, 1 and 0, 0. So so the diagonal items here might be the probabilities, right? Because if I take a look at the measurement probabilities, I see that I have for the state 0, 0, 50%, for the state 1, 1, 50%. So we've basically created we've basically created a Bell state, or a type of state where the two qubits are always going to agree. So I'm assuming that's what it means here. Because if I remove that, interesting. Oh, sorry. If I apply a Hadamard to both, so you've got the same probability, 25% for each possible state. Something seems to be a bit off with rendering, and I don't know. I hope it's not because of the screencasting that I'm using here. It's messing up with. I think it's messing up with the labels. It's been a bit buggy recently, but I mean, I get it. It's supposed to be a better thing. So, okay. So if I go to density matrix again, but then those things here, what do they mean, right? So 25%, 25%, 25%. So sorry, 0, 25, yeah, 0, 25, 0, 25, 0, 25, 0, 25 of. You see that I think those labels, it says 1, 1, 1, 1. I think that's wrong, right? I think that should be 0, 0, 1, 1. And I would interpret that as how much they agree or disagree. I mean, I'm assuming that has to do something with that, but I don't know. So, but this tell me basically, I think that those map to the measurement probabilities. So what happens? So now we know what happens if we do a control knot. Because maybe a good way to understand the control Z is to figure out figure it out in relation to the control X. Maybe that's one angle that we can approach it from. So this is a control knot on a qubit that's in a superposition, like 50-50%. So basically, it means they now become entangled because the measurement of this qubit is going to affect the measurement of this one. What happens if I replace that with the control Z? What? Interesting. That is in the. So basically, what this is telling us is that and what is the measurement probabilities? 0, 0, and 1, 0. 0, 0, and 1, 0. So what this is telling us is the control Z does nothing really, because the control Z does nothing to a qubit that is a 0, right? That's my understanding. That's my understanding of what the Z does. Because if I remember well, don't we have a block sphere or something here? It would be cool. It would be pretty cool. Because the control X basically flips a 0 to a 1 and a 1 to a 0, but the control Z flips the plus state to the minus state. So if your qubit is in 0, you're not gonna, nothing's gonna really happen here, right? So, just by doing the same that we do with the control X, it's not gonna give us some interesting insights, because basically what this is telling me is that the two probable states are 0, 0 and 1, 0. This means that this is somehow at all not affected, and that's not a type of correlation that makes. I mean, it is a type of correlation, but I'm not so sure how useful that type of correlation is. It's a type of correlation where the target qubit is always going to be 0. But yeah. So if I add a Hadamard gate here, now that can get interesting, because now this could be both these zeros and 1. Let's do it differently. Let's say that this is that we turn that thing into 1. So we do with this with the next gate. So now we know it's a 1. So I hope that's not buggy. It's weird. Nothing changed. Red. Huh. I think so. This has to do something with the. This might have to do with the face. That is actually a pretty cool tool. This is really awesome. Like, this is really awesome because you don't have to do manually, the zeros and ones thing, and you can just basically say probabilities and the state. The state vector. Okay. So the colors probably are, and you see what's cool is that they tell you. So this is decomposed into probably the pure, like, sort of the amplitude and the phase. If that's, I don't know. If that's really what it means. Complex argument. Yeah, the color is based on the complex argument. Complex argument meaning the imaginary argument. Okay. Let's go back to the density matrix. Again, it's not the first time I see this interface. I've been playing with this for a while, even before I started shooting all the videos, but I've never fully grasped everything completely. So that's also going to be helpful. So what happened here is that it's the same thing then without an X, but it basically changes the color, which it means it changes the. I don't know if it's correct to say that it changes the phase, right? Because it's just there's a minus now, and the color indicates that as well. So from probabilities perspective, we've got the same thing. What if let's see if I remove that. What? Interesting. So I like the color things here because they definitely can help you visualize some interesting stuff. But how can that be? So look at this. So now we've got 0, 0. If I add a control X, that here, that doesn't change. It doesn't change because, wow, that's super weird. That's even worse than I thought. Because that doesn't change, it makes sense. The control bit is 0. The control bit is 0, right? So that's not going to be activated. Whereas if I add a control Z, what the hell is that supposed to be? How is that possible? How is it possible that that is anyhow taking any effect if the control bit is 0? This is, boo. I think that's going to take quite some. It's gonna span across some different video sessions because that's definitely going to be. So that's the first thing that I want to figure out. What is happening here? So let's take a look at the measurement probabilities. So what? That's it. You basically have a superposition. So you basically have the same, like if you do this. No. Oh, wait a second. In an article, I think it was here. So here, there's an article about that where basically I think here James, yeah, I just checked his name. James tries to explain. Yeah, I think this is what I want to get. Okay. So it's basically saying that the control Z is the equivalent of doing that. Now I see the version of the IBM Career Experience is already, more advanced than when the article was written, because now there is actually indeed a sign for that. So, but if I do that, let's check that. So if I do this and this, so there must be something off here because it's not possible. because that's still 0, 0. Why would that be the same? This is almost exactly the same as explanation. The only difference is that the x might be applied rather than the z. In this article, we gave 3 different explanations as to how the CZ works. The CNOT either does nothing to the target qubit or does an X gate to it, depending on what the target is doing. This is almost exactly the same as our explanations of the CZ. The only difference is that it is an X that might be applied rather than a Z. And since we know how to turn an X into a Z, we can now turn a CNOT into a CZ. Yeah, but then there must be something off with this interface right now, because that makes total sense. This is 0, so nothing happens, right? So the density matrix stays the same. Whereas if I remove all that, and I add a control Z, and that shouldn't happen. Maybe I should save that and refresh. I might be looking super stupid if someone's like, obviously that's obviously what you're gonna expect, so it's not a mistake. But it just doesn't make. It's gonna refresh. Let's see what happens. Seems to be the same. Control Z. Density matrix. How? How can that be? How can that be if they're both 0? This means this doesn't get applied. I won't understand ever. So now there is a 1, right? So now there is a 1. So now we turn that into a 1 and we say do a control Z on a 0, and then and still that's what happens. And if we do that like this, so maybe I'm not seeing this from the right perspective. Maybe that's a bit fooling here because of the measurements that we should be doing. Because if we do a I'm gonna just put that here to make it like a clear that I'm making a measurement now, and I'm gonna make a measurement on the Hadamard base for both qubits. And how can I make sure this runs on a simulation and not on the simulator? And let's say 1,000 shots was saved. Pending results. Okay. But I can kind of see the intermediate results here or not. What does it change if I do that? I mean, I should be able to see intermediate results if I pretend that I'm going to measure in the Hadamard base. If I'm doing that, so now I'm going to be measuring the Hadamard base, but that gives me the same as I was seeing before. And if I'm going to measure in that other base that they talk about in the article, the this base, so I'm going to do an S transpose, if that's how it's called. That is super weird. Okay, what? But that behaves like the Bell state. Oh, maybe. What this is doing is creating sort of the equivalent of a Bell state, but on another computational basis. So, maybe that's what's happening. Is there a way I can find like an interactive block sphere? Because that would definitely be helpful. Block sphere plotting, university. Come on, I'm not going to download anything now. Someone should do that. That's definitely QC simulators. Hmm. Whatever. Because so what the S is doing, right, is basically, so the S is like the, if I understand S well, it's like half the way. It's half the way the Z, right? Whereas S transpose would be then half the way the Z, but on the opposite direction. Um, um, mm, 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 mm. So by doing that, because I'm having maybe I'm trying to visualize something that I shouldn't even try to visualize because it's just complex. But basically that be, ooh, wait a second, what the, so now we've got, what is that then? Is that the imaginary? Okay, RE for real probably, and IM for imaginary. So that's probably the complex. That's probably the complex. That's pretty cool because look at this. Look at it. Whoa. Okay, let's do it. Okay, but look at this. No. Okay, so we've basically shifted information, and that's what was pretty cool. Shifted information from just the real density matrix to the imaginary density matrix. So what's going on here is basically the if we measure this way, it's still for me confusing. Okay, that this is doing anything in here, honestly. If so, this is 0, 0, and this is 1, 1. So that's basically again that type of entanglement where they always agree. But if you look at it from that perspective, then you're basically getting the same thing, but from another computational basis. But I mean, it triggers to me the same question: how useful is that intuitively to build algorithms or to do stuff? Because this is what I don't understand. So this is what I don't understand, is that this basically, if I take a look at the state vector, what I see is that there is a minus here, right? So you see that it's equal probability of all of them, but the 1, 1 has like a negative phase. So that could be useful because it's like you're flagging something, maybe in terms of flagging data for your algorithm or whatever. That was way more overwhelming than I expected. Why is this untitled experiment? Were these results ready? Completed? What happens if I click? So I see the circuit, and then I'm going to see the results. Yeah, but that's what's super weird. How? Okay, but that really seems like there was no mistake. So how is it possible that? Oh wait, because I just did it like that. I just added the Haramarts. Let's see. Let's see if I do this. What's actually happening? So why is this? So if I move the Z here and I move the Z here, and now I run that, I want to make sure that there's no sort of mistake in that visualization, because that's going to make it difficult for me. It's going to make it difficult for me. Good. Let's see. And that's, already completed a few seconds ago. Oh, so something's off, man. Something's off with that. Maybe maybe something's messing up with it. Maybe the fact that I'm using that thing with an overlay. Maybe I'll try to close the tools. Maybe that will help. Let's see, because that's definitely 0, 0, right? So okay, so that sorry for that. That's definitely there's definitely something else going on here with these visualizations, that it's either a bug on their side or it's me messing up with, because that shouldn't be like that. That should not be like that. It definitely should not be like that.